All right, so as always, I'm going to be recording us going through these notes and talking about them today. And then once I finish up and the videos get all posted and uploaded, then I'll post them right here in the chemical reactions part of the Zoom notes section. And then the notes that we're going over today, I made sure to open them up on Sunday or Monday, I think, so that everybody could look at them early if they wanted. Well, we're going to be talking about chemical reactions. So we'll go over things like how you can tell that a chemical reaction is happening, how things like energy and matter are conserved from the beginning to the end of the reaction. And we'll talk a little bit about a couple of specific types of reactions that have these cool names, exothermic and endothermic reactions. All right, so chemical reactions, our notes, our new topic that we're going to start covering today and tomorrow too. Tomorrow will be kind of a more in-depth look into a part of what makes a chemical reaction go. So we've actually already talked about chemical reactions a little bit, but when we talked about it earlier, we called them as chemical changes. So chemical reactions are just a different way of saying a chemical change, essentially. So whenever we have our substances, our matter, that does some sort of chemical change from one form to another. So to remember when we talked about chemical changes a couple weeks ago, the big point that I stressed on was we start with one thing and we end with something different. So when we go through that whole process, when we take our starting material and chemically change it into our ending material, that process is called a chemical reaction. So we're taking one set of chemicals and then turning them into something new, something different. So there's some common sort of everyday chemical reactions that you might not even realize it pictured over here. And it includes things like growing. So as this caterpillar eats this leaf over here, he's going to take in the substances from that leaf. His stomach is going to break those down and get all of the sugars and carbohydrates and stuff that he needs. And then the cells in the caterpillar's body will turn those substances into chemical energy. And so we've taken leaf material and turned it into caterpillar energy material, which is then used for moving, growing, reacting to their environment, stuff like that. So the reason why you are not the same size as right now compared to when you were born, hopefully you're a little bit taller than back then, that's due to millions of chemical reactions happening every day in your body, taking the food that you eat and changing it into energy and new material, new body parts. Ripening is also a chemical reaction. So like you have this mango, they start off growing, and when they first develop on the tree, they turn green, but then over time, or maybe this is a tomato. This could be a tomato. So maybe it's a tomato that started off green, and then as you let it sit on the vine, it went through a series of chemical reactions where it ripened, it changed color from green to red, and the taste changed as well. That's because we have a different set of chemicals inside the tomato now compared to before. Same thing with something like a banana, right? So you buy a banana from the grocery store and it's all green on the outside. And if you were to eat it, it's really kind of starchy and chewy and it tastes kind of like a banana, but maybe not that great. You let it sit for a couple days, it changes to yellow skin on the outside. The inside is a little bit softer and sweeter. If you accidentally let it sit too long on your countertop, it'll turn brown and the inside will get kind of sticky sweet and really brown and mushy. That's due to chemical reactions changing the outside and inside of the banana from one set of chemicals to another. So one set of chemicals produced a green skin and a really starchy, tough inside. Our final set of chemicals produces a brown or a yellow skin and makes it much softer and sweeter inside. So we're changing substances inside the banana, and they're going through these chemical reactions. So decomposing is kind of similar to growing, only it's things like mold and fungus that are growing on our food instead of little animals and plants growing up to be big and tall, right? But this bagel or donut or whatever in the world it used to be is having all of the starch and flavor molecules in it broken down and consumed by the mold and bacteria that's growing on the bagel, and they're turning it into energy. And so just like with the growing, we're breaking down one set of chemicals and changing them into a new set of chemicals. We're breaking down bagel chemicals and turning them into cellular energy chemicals that this mold or bacteria is using. And then finally, one that we talked a lot about when we were talking about chemical changes is combustion or burning. So you set a log fire. The chemical reaction is what's producing all of the heat and the light that we're feeling and seeing. And then we go from starting off with a bundle of logs in our fire pit to, at the end of it, having a whole bunch of smoke that went up into the air and a lot of ash down here at the bottom of the log. So this combustion is a chemical reaction. We're taking one set of the substances, the logs, and turning them into new chemicals, new substances, smoke and ash. So chemical reactions are when we are changing the chemicals. We end up with different chemicals compared to what we started with. So what are some ways that we can see a chemical reaction happening, or that we can detect that a chemical reaction happens? Yes, Dasani, you got a question.
Yeah, I'm kind of late, but you said smoke, but don't smoke turn into like fog and stuff like that, and then it turns wet, get moist, and then it's drippy and stuff like that, like water. But it turns to anything smoke. It could turn to a cloud.
So you're
we use it that, like we use the smoke for. Ain't that?
Smoke from what?
Okay, never mind then.
Sorry, you're cutting.
Smoke like from like this anything like. My background to but like smoke is like fog and stuff like that, and then it's like moist and stuff. That kind of smoke. Are you talking about like the foggy smoke and not the clouds?
Okay, I got you.
I mean, they all a chemical reaction. If you ask me, because if it's 1 minute it's cloudy and then it's full of smoke somewhere, and then it turns into another chemical reaction, like a fog turn into something moist, or it makes you moist. Like say for instance, I'm in the shower and then all the smoke come around me, and then I look in my mirror and get watery.
Gotcha.
Like that type. My bad. Okay. My bad. I'm being like off. Yeah.
So what you're experiencing is actually not a chemical reaction, because all of that fog, that mist that's coming from the hot shower or from the like fog and the air outside, like if you go out driving early in the morning and it's hard to see because of all the fog, all of that is actually just water vapor. So it's coming out of your shower because your shower is very hot and it's causing the water vapor to kind of spread throughout the room and latch on to like the mirror and windows and stuff that might be in your bathroom. Same thing with fog. So fog is essentially just a cloud that is way closer to the ground compared to when it's usually up in the air. But a cloud is also just water vapor that is either that's closer together than it normally would be kind of out in the normal atmosphere. So a cloud is when you take a whole bunch of water that's kind of dispersed in the atmosphere and kind of clump it up into one area. So it's still water, right? You're not changing it from water to something else, but you're just making it either more dispersed or more clumped into an area. Whereas smoke coming off of a fire, on the other hand, is a new set of chemicals that was not in the air before. All right, good question. So, some signs that a chemical reaction might be going on. So bubbles appear or a gas forms. So this would be like when you put like an Alka-Seltzer tablet into a bottle of water, and then you see all of that fizzing and stuff start going on. Same thing with if you've ever mixed vinegar and baking soda before, and it makes that kind of huge explosion of bubbles and foam. That's due to chemical reactions. So the bubbles are appearing because we're creating a new gas that didn't used to be there. It's kind of similar to the smoke from fire. So because of the heat in the fire, we're giving off smoke into the air. Because of the way that the chemicals are reacting and different sorts of reactions, we might be giving off gas that forms as little bubbles in the solution. On the opposite side, something that can happen, although it's usually not quite as common, is you get a solid that forms. So in fancy chemistry terms, we call it a precipitate. But essentially, it's if you mix two like different liquids together, and all of a sudden you get a new solid that starts to kind of form on the bottom of your glass. So this is not like if you put a little bit of sugar in water and then dissolve it and then add a lot more sugar in and that sugar won't dissolve. That's not what we're talking about here. By this, we're talking about how you just add usually it's two different liquids to one another, and then all of a sudden a new solid forms that didn't used to be there before. Like I said, that one is a little less common, a little more rare. Color change is a great example of chemical reactions. So, like I said, there's some good examples of this and some not good examples. Some good examples would be like with the ripening that we talked about earlier, how your tomato goes from green to red on the vine, or your banana goes from green to yellow to brown when it's sitting on your counter. Those are color changes due to chemical reactions. What we do not mean by color change is you take a big thing of water and you add in some purple Kool-Aid to it and stir it around, and now you have purple in there. That's not the kind of color change that we're talking about, because you added that color on purpose, right? You added that purple powder, and so now your water is obviously going to be purple. This color change is where we didn't add anything extra, or we added two things that maybe were like clear. So some clear chemicals, when you mix them together, they'll all of a sudden turn into a certain color, like they'll turn pink, for example. So that's the kind of color change we talk about, either a color that changes over time or that happens when two chemicals that do not contain a certain color are mixed together, and now all of a sudden a new color is there that was not there before, right? So remember, we're all talking about stuff that wasn't there before, but then all of a sudden is there now. So a temperature change can be a good example of chemical reactions. So either an increase or decrease in temperature. So for example, like fire is a great example of temperature being given off. Also, We don't really have these down here in Texas because we don't need them. But I lived in Ohio for 5 years. And during the winter, I would use these little hand warmers, which came in these little packets that when you were ready to use them, you'd squish them up and then stick them in your glove. When you squished up the hand warmers packets, that would start a chemical reaction that gave off a lot of heat. So it would keep your hands nice and toasty inside your gloves when it was like 11 degrees outside. You can also get decreases of temperature in certain types of reactions. And we're actually going to talk about some cases where that could happen a little bit later on in the notes. So light also being given off is another good sign that a chemical reaction is happening. So we already talked about with fire, that gives off a lot of light. Same thing with things like fireflies. The reason that fireflies light up at night is not because they're starting a small fire inside of their abdomen. It's because they have special proteins and chemicals inside their abdomen that when they use the proteins to break the chemicals apart, light gets released. So getting some light where you didn't have light before, also a good sign that a chemical reaction is happening. And then finally, sometimes it can be a little bit harder to detect, but if there's a big change in the smell or the taste of something, so this happens a lot in baking, right? You mix all of these different weird things together, like flour and eggs and sugar, that on their own, if you just like cracked an egg open and ate it, and then ate a scoop of flour and ate a scoop of sugar, gross, right? Disgusting, not good. But you mix them all together and you put them in the oven, and the heat from the oven combined with the mixture of the batter gives you something very tasty and good to eat. Same thing again here with that ripening fruit that we were talking about earlier, right? A green banana that you just brought home from the grocery store compared to a yellow banana that's been sitting on your counter for a couple days is going to taste a little bit different, right? That's because of these chemical reactions, changing the chemicals and changing the taste. So here's an example of like some bubbles being formed at the bottom of this reaction. Besides fireflies, another good example of light being given off is in certain species of jellyfish also have those special proteins that'll light them up at certain points during the night. This has its own special word when it happens inside of animals and plants called bioluminescence. So we're making light inside of a biological organism like a plant or animal. So these are the 6 signs that some sort of chemical reaction is occurring. There could be bubbles that appear. You could get a new solid that forms in the bottom of your tube. You could get a new color. The temperature might go up or down. There could be some light that gets given off. And you could end up with some new changes in smells or tastes that were not there before. All right. Any questions about chemical reaction stuff so far? All righty. So when we want to show what a chemical reaction looks like in terms of the atoms that are actually interacting with each other, we can show it as sort of like a math equation, right? So we're taking one or more substances and turning them into new substances, just like how in math, we start off with one set of numbers and we end up with a different set of numbers. So in chemical reactions, our 2 different sets of chemicals are given 2 different special terms. So the reactants are our starting material. These are, just like their name suggests, the substances that are going to react together. So we start off our chemical reaction with our reactants. Those are our initial starting chemicals. We then go through the reaction, go through the chemical changes that are going to happen, and then end up with our new chemicals, the products. So again, just like their name suggests, the products are the substances that are produced at the end of the chemical reaction. So the way that we tend to write these out in chemistry is that we have the reactants on one side of the equation, and then instead of an equal sign, we use this arrow to kind of show that they're changing or producing the products. So the reactants react together, the products are produced. Reactants are the starting material, products are the ending material. So this is what we mean when we talk about how chemical reactions are these changes. The reactants and the products have to be different, right? If they're the same thing, then we don't have a chemical reaction going on. So whatever reactants we have, we'll end up with some sort of different combination of them in the products. So one very famous reaction is the photosynthesis equation, which is the chemical reaction that explains how plants take sunlight and carbon dioxide from the air and water from the soil and turn it into energy for their cells, turn it into sugar. So the reaction that comes up is going to be big and long and complicated and scary looking. Don't so much worry about what all the different individual little pieces mean. I'll kind of walk you through each side. But there are going to be a couple things that I point out as we go along that I want you to pay attention to. So here is our photosynthesis equation. And actually, let me fix it a little bit. Some of the wording got a little bit off. All right, there we go. So on our reactant side of the equation, we have a couple basic compounds that we were talking about last week. We have carbon dioxide right here, CO2, and water, H2O, right here. So carbon dioxide and water are our reactants. And then when there is sunlight present, so when it's the daytime, when it's a day like today, beautiful sunny day, the sunlight causes this reaction to happen, and we change the carbon dioxide and water into something new. Instead of CO2 and H2O, we end up with oxygen gas, O2. So this is why plants are so important to our world, because they give off oxygen that we need to breathe. But that's just a byproduct. That's just something that they happen to make. The main thing thereafter is this big molecule right here, this big compound, C6H12O6, also known as glucose or sugar. So if you know people who have diabetes, their blood glucose level is something that they're always keeping an eye on and have to be worried about. And glucose is just one of the most simple forms of sugar that exists in nature. And so we have our reactants, carbon dioxide and water, CO2 and H2O, and we have our products, glucose and oxygen. Two different compounds, C6H12O6 and O2 for the oxygen. So again, reactants, they react together. Products, what are produced. We're going through a chemical change here, right? We end up with different chemicals than what we started with. Something else that I want you to notice is that we have the same types of atoms on each side of the reaction, right? So over here, we have a C, we have an O, and we have an H. And then we have the same types of atoms on this side. We have a C, we have an H, and we have some O's. So in a chemical reaction, while we may make new chemicals, new substances in the products, what we cannot do is make new atoms, right? Notice there are no atoms over on the products that we did not start off with in the reactants, right? We didn't all of a sudden get a nitrogen mixed in over here, right? There's no neon or aluminum that got added to make glucose or oxygen. Instead, all we did was rearrange the atoms, right? So we can't make or destroy atoms, right? Instead, all we can do is rearrange the atoms that we have into a different setting. So as this reaction happened, it took the C's, O's, and H's from the carbon dioxide and water and rearranged them, remixed them into C's, O's, and H's to make glucose and oxygen. All right, so we didn't add anything. You'll also notice that we didn't get rid of any atoms either. So there's a C on this side and some C's on this side. There's O's over here, there's O's over here. There's H's over here, there's H's in the products. So we didn't just end up with C6H12, right? Because we still have those oxygens from before, and these oxygens need to do something. So chemical reactions just rearrange the atoms. They don't add in any new atoms to the products. They also do not take away any atoms from the products. So whatever different atoms that we start with, those have to be the atoms that we end with. So that's sort of the basics for how we write and read chemical reactions. We look at our reactants, we look at our products, and we can determine how do we go from this to this. In this case, we can see that we rearranged the C's, O's, and H's to go from carbon dioxide and water to glucose and oxygen. All right, so reactants, products, and the atoms just got rearranged. We didn't make or get rid of any new or old ones. Oh, okay, you wrote it in on the slide. So just like how atoms are conserved in our reactions, right? Since we only do the rearranging, we don't make or break any atoms. Same thing with the amount of energy that happens. So we can't create or destroy any new energy in these reactions. Instead, it gets transformed from one type of energy into a different type of energy. So we have the same total amount of energy at the beginning and end. It just looks and is used in a different way as the reaction goes along. Same thing with our atoms from before. We have the same types of atoms from beginning to end. We just rearranged who they are bonded to. So in a super simple example of this, if we have this basic light bulb right here, and we take 100 units of electrical energy and send it to that light bulb. This is kind of an older, old-fashioned light bulb. It's not very efficient. It gives off light and it produces a lot of heat, right? If you've ever gone to change out an old light bulb and it just got turned off, you're gonna burn your fingers, right? Because light bulbs get hot if they've been on for a long time. So from the 100 units of electrical energy that went in here, 5 of those energy are used for the light that the light bulb produces, and the other 95 get transformed into heat. Again, we end with 100 units of energy, and we started with 100 units of energy. It just got transformed throughout the course of the reaction. Same thing with the atoms. We start and we end with the same types of atoms. We just transform what they look like, who they are bonded to. So in that photosynthesis example that I was talking about, we transform energy from one form into another. Right, I mentioned that we start off with carbon dioxide and water, which are gases in the air or liquids from the ground. And then we combine that with energy from the sun. And then energy from the sun, the light and the heat that's coming out of the sun, are what allows the plant to transform those atoms into sugar and other structures that it needs. So sugar is a type of chemical energy because when we eat the plants, so when we eat these fruits, we use that sugar that's present in there in order to power our own bodies, right? So plants will use the sugar that they make in order to give themselves energy. And then when we eat the plants, we use the sugar that they've made in order to give ourselves energy. So we've gone from light energy from the sun into chemical energy that can be used by the plant or that can be used by us when we eat the plant. So we're transforming the energy from one type to another, just like we're changing how the atoms are arranged from one set of structures to another one. But we still have the same energy and the same types of atoms at the beginning and the end. All right. Any questions so far on chemical reactions, rearranging the atoms, transforming the energy, anything like that? Any questions about any of that so far? All righty then. So the last couple things that I wanted to go over with you guys today was a couple different specific types of chemical reactions. One of them is called an exothermic reaction. So exo is a Latin prefix that means like giving off or going out. And then thermic is like thermal, so like heat. So exothermic, heat going out. So this is reactions that release energy to the environment. So usually these are reactions that produce things like heat and light. So in general, because of the energy that is going out from these reactions, the air around where these reactions are happening heats up because it absorbs that energy. So that's where the heat comes from, is absorbing the air, absorbing the energy. So we've already talked about a couple different types of exothermic reactions. We've got digesting food. So like we were just talking about with the sugar in the plants with photosynthesis, we eat the plants and break down their sugars. Breaking down those sugars releases a lot of energy that then we use in order to power our bodies. So the reason why you're able to get up, move around, why you have an internal temperature that's a lot warmer than the temperature outside, right? So hopefully everybody, if you're feeling okay, should have an internal temperature of 98.6 degrees Fahrenheit compared to the outside temperature, which today I think is only getting up to like 77, 78 degrees. So the reason why we have a much higher internal temperature is partially due to breaking down the energy that's contained in the food that we eat. That decomposition that we looked at earlier, so like the mold and the bacteria breaking down a piece of bread or a bagel or something like that, also is exothermic. So the mold and the bacteria are using the energy that they get from decomposing that food. Obviously, combustion is a really big exothermic reaction. So whatever you burn, it's going to create a lot of light and a lot of heat from the fire. And then also things like the lightning bug and the jellyfish that we were talking about earlier that can glow at night, those are also exothermic reactions. So it doesn't have to be only heat that gets given off. It can also be light or some sort of combination of both. So anytime that you're releasing energy into the environment, you're breaking down something and causing that energy to be released. That is an exothermic reaction. Heat going out. On the flip side of that, if you're absorbing energy, that's when you have an endothermic reaction. So endo, again, a Latin prefix meaning like into, going inside. So this is where you absorb energy during the course of the reaction. So generally, if we're building a whole bunch of big structures, a big chemical, that is an endothermic reaction, right? So those chemical bonds that we were talking about earlier, the covalent bonds and the ionic bonds, it takes energy in order to get those new bonds to happen. So to go from one set of chemicals and break them up and reform them into something bigger, that requires energy from the environment. So it could be absorbing light energy, like in photosynthesis, right? Where the sunlight allows for the carbon dioxide and water, which are two kind of small chemicals, to be built into sugar, which is a much bigger substance, a much bigger chemical. So we're absorbing energy from the sunlight in order to create these glucose molecules. So it doesn't necessarily mean that the temperature gets colder, right? If you go and hover your hand over a plant, you're not really going to feel the temperature drop because these reactions are going on. But it is possible. There are some chemical reactions that do cause a drop in the temperature around them because of all the energy they are absorbing. Right? So when we're absorbing energy, when we're building structures, making lots of chemical bonds, we have an endothermic reaction. If we're releasing energy, we're breaking down, we're breaking apart bonds, we're decomposing and digesting stuff. Those are exothermic energy reactions. We're creating energy, we're releasing it into the environment. All right. Any questions about exothermic versus endothermic reactions?
No.
All right. Alicia sounds all good, and it looks like nobody else has any super pressing questions at the moment. So your homework for today and tomorrow goes right along with these notes about chemical reactions and energy. So let's go take a look at that real quick. So for today's assignment, if you haven't looked at it yet, It's very simple. Essentially, all I want you to do is list out the 6 signs that a chemical reaction is occurring. So if you want to go back and look at the notes and look in one of those early slides, I talked about all the different ways that you could tell that a chemical reaction was going on, like bubbles being formed or heat being given off or a color change happening. That's what I want you to list for the assignment that got posted today. And then tomorrow's assignment is equally pretty straightforward. It's essentially just, I want you guys to compare and contrast exothermic and endothermic reactions. So tell me a little bit about each one. What are the characteristics of each one of those types of reactions in terms of what they do for energy, what types of reactions are generally exo versus endothermic, stuff kind of like that. So those assignments are hopefully both pretty straightforward and fairly simple, because on Thursday is when we're going to start talking about chemical equations more in depth, specifically how to balance chemical equations, how to make sure we have the right number of atoms on each side of the chemical equation. And that is a lot kind of more tricky, and it's going to take a lot more of us talking about stuff and going through stuff. Plus, it's always nicer to kind of start the week on an easier note. So as always, if you want to go back and look at those notes that we just went over, they're right here under the Tuesday Notes Chemical Reaction section. And once we're done with today, I'll make sure to post this video of me going through the notes up here under the Chemical Reactions Zoom video section. All right. Any final questions about chemical reactions, work for this week, anything like that? All